Good morning, everyone. This is Noushath Shaffi. I'm here to present a paper entitled CoMRIAD for Alzheimer's disease detection. Myself, Noushath Shaffi from Department of Computer Science, College of Science, Sultan Qaboos University from Sultanate of Oman, co-authored by Mufti Mahmud from KFUPM, Saudi Arabia. This work has been accepted at the third Muslims in ML workshop co-located with NeurIPS' 2024. Traditionally, Alzheimer's disease detection using deep learning has been carried out by considering any of the single planes. For example, the dataset can have MRI dataset can have coronal plane or axial plane or sagittal plane. So far all the works, most of the works have been carried out by considering any one of these planes only, and mostly axial planes, because the traditional datasets that are available in the public platform is considering only axial planes. So in this work, what we have done is we try to combine all the three planes of a subject and applied deep learning algorithms on each plane, and we try to combine the results of these planes to enhance the classification performance of the deep learning frameworks. So the main contribution here is we propose a novel deep learning based pipeline called CoMRIAD, which combines three planes, coronal, axial, and sagittal, and we referred it as combi-plane approach for enhanced Alzheimer's disease detection and classification. Our experiment results demonstrates that CoMRIAD outperforms single plane MRI analysis, achieving at least 6 to 8% increase in overall accuracy for two-way as well as four-way classification task. So we have performed both classifications, binary classification as well as four-way classification of Alzheimer's disease, trying to detect different stages in dementia. The four stages are Alzheimer's disease, which is the end stage of the disease, and then in between we have mild cognitive impairment, MCI, late mild cognitive impairment, and cognitively normal. So these are the stages of this dementia disease, and we are doing both four-way classification as well as binary classification, given an image whether the patient have Alzheimer disease or no. So this is the pipeline you can see here. Traditionally, the patient undergoes some kind of scanning. Scanning can be PET, fMRI, MRI, and once the images are obtained and the models are trained, so this box indicates some deep learning models, different architectures. So in our case, what we have done is we have taken the convolution neural networks and especially the MRI block. So here the highlighted block indicates the actual contribution of our paper. So what we have done is we have taken out of all these biomarkers, we have considered 3D MRI, and from 3D MRI, we obtained all three planes, and on individual planes, we apply convolution neural network, and we get the classification results from each plane. Now the classification results are actually combined to get the final classification results. And also, as you can see here, to enhance or to get the interpretability of the results obtained by this deep learning networks, which is often considered as black boxes, we consider the final convolutional layer, and we obtain GradCam heat maps, and we try to obtain some affinity between the heat maps obtained with the predicted labels. So this is the experimental result. First, what we have done is we have considered the ADNI dataset for experimental purpose, because ADNI dataset has not only the three planes of MRI for every subject, it has all the clinical parameters and different biomarkers like CT scan, PET, and clinical datasets. So we have considered MRI ADNI dataset, and from that we have considered MRI planes. All the three planes we have considered. So what we have done is once we have extracted the MRI images, we split the dataset into 70 and 30%, 70% for the training dataset and 30% for the test dataset. You can see here 70% of the data has been trained, and from the remaining 30%, what we have done is we created triplets of the images from each plane, coronal, axial, sagittal. That is actually this combi plane. Individually as well as combi plane wise also, we have extracted the results. So individual results are for every plane is noted down here in this table. And what we did is like the triplets that we consider from each plane to form the test base for the combi plane approach, we increase it in terms of 1000, 2000, 4000, and 8000. And you can see here the combi plane approach significantly outperforming the individual plane approach. You can see here by at least 6 to 8% of increase we can see here, not only in the accuracy as well as other performance metrics like specificity, sensitivity, false negative rate, false positive rate. You can see here false negative rate and false positive rates are significantly low in the combi plane approach for different number of input cases. Now this image shows the combi plane approach confusion matrix. You can see here this is the confusion matrix drawn for 4000 images. Coronal plane has the confusion matrix of this, and sagittal and axial planes also obtained confusion matrix of these figures. Now, using the combi plane approach, this is the result of the confusion matrix obtained when we combined all the three planes. You can see here there is a significant increase in the correct classification of the four classes. So this result shows that the combi plane classifier considers the subtle patterns that are observed from all the three planes and combines them to make a more accurate classification for the Alzheimer's disease. And also when we go to a clinician will not only see a single plane like the traditional deep learning platforms carry out the task. So we are trying to do what clinicians traditionally do. They take the MRI and they see the disease pattern from all the patterns. So we are trying to mimic what the clinicians do to diagnose the neurodegenerative diseases like Alzheimer's disease. Okay, so here this is an example experimental result for binary classification of the disease between different dementia stages. You can see here the first one is about early mild cognitive impairment versus late mild cognitive impairment. The easiest binary classification is between Alzheimer's disease and cognitively normal cases. What is more difficult is to differentiate between the stages of the late stages of the dementia like MCI and EMCI. It's very subtle different. It is very difficult even for the clinicians to observe the pattern or to tell in which stage the patient is currently undergoing. If you can see here, the green bars indicate the results obtained by the combi plane approach. You can see here the false positive rate, false negative rate is significantly low in every binary classifications that we have carried out here. Now this is to the clinicians will be only happy if they know why some results are why some results are coming in that manner. For example, they know it has been a particular image has been classified as Alzheimer's disease, but they should also know the associated reasoning behind that classification by the deep learning framework. So here we try to extract some explainability, and we applied GradCam explainable interpretability framework for generating the heat map. And what we observed here is the red regions in the overlays. So this is the heat map from the GradCam, and when we overlaid this heat map on the original image, we get this third row images where red regions in the overlay signify a close affinity to the predicted class. The axial plane here highlights regions associated with neurodegeneration, atrophy, or abnormal metabolic activity in Alzheimer's disease. The coronal heat map here focuses on cortical areas like the temporal and parietal lobes commonly affecting in the Alzheimer's disease. And finally, in the sagittal plane, the red region highlights vulnerable regions like the prefrontal cortex and posterior cingulate cortex. So by examining all the heat maps, clinicians can gain insights into how the results affect the AD-related changes in the brain. We also computed paired t-test to test the significance of the results. The obtained p-values here, the last column, imply high statistical significance, confirming increased reproducibility of the method and reflecting a consistent pattern of the results rather than the results coming as a random chance. So this statistical test confirms that the pattern of results are consistent and they consistently outperform individual plane approaches. So the key findings here are the increased accuracy of 6 to 8% compared to the single plane approach, and also we conducted paired t-test to test the significance of the results. Heat maps generated using GradCam and Pearson correlation coefficient computed between the original MRI and heat map show high affinity to the predicted class. There is one limitation to this approach, which is increase in the computational cost associated with the processing multiple planes to achieve enhanced accuracy. So multiple plane means increased resources in terms of increased number of parameters, the memory and computation to learn those parameters, storage and deployment in real time. So this is all some real-time limitations of the proposed approach, but some kind of optimization could be incorporated in future work to mitigate these limitations. So this is about our work, and please feel free to contact us for any questions that you may have, and also we have provided GitHub link for our code. Those codes should help reproduce the results that we have reported in this paper. Thank you.